Normally, light travels in a straight line, but when it passes from one medium to another, it likes to change its path. It might seem like an absurd idea, but you have certainly witnessed it at least once in your life. Let's look at an example. Have you ever noticed how a straw looks bent when you place it in a glass of water? That's refraction in action. The light rays are bending as they move from air to water, creating that optical illusion. It's a neat trick that nature plays on us. But how does it happen? And is there a way to predict the new path it's going to take? Luckily, physics always has an answer. In the year 1621, Willebrord Snellius, a Dutch mathematician, made a really useful formula just to explain light. Today, I'm gonna be your physics teacher for the first time. Because in 10th grade, I studied this phenomenon and it sparked some interest in me, and so I made a refraction simulator in Python. This video is a little different from my other videos, so I really hope you like it. And if you did and want more videos like this one, make sure to leave a comment and perhaps maybe a subscribe. In your code editor, start by creating a new Python file. Then you need to import Pygame, which is a library that allows us to draw on the screen, and you also need to import everything from math. We'll start by defining a couple of values, such as the screen dimensions, the background color, a grid color, and the color of the ray of light. Before we continue with the code, I need to explain how refraction works in simple terms. For this example, we'll imagine a single ray of light passing from air to water. This part is called the incident ray, and it's going to enter the water with an angle relative to the normal, called the angle of incidence or alpha. But instead of continuing in a straight line, according to how light normally travels, the angle changes and it bends. This new ray is called the refracted ray, and it also has an angle relative to the normal called the angle of refraction, or theta. But why and how does this happen? Basically, light changes its speed when it passes from one medium to another. This change in speed makes the light change direction. But you may ask, why does it change speed? Isn't the speed of light a constant? The answer is no, because the speed of light depends on the density of the medium it's passing through. Therefore, light travels faster in the air than in other mediums such as glass or water. In order to translate all of this information in ways we can work with, we need to do some math. And for that, we just need one simple formula, Snell's law, which describes this phenomenon mathematically. In this formula, we have four numbers. N1 and N2 are called the refractive indices of the two mediums respectively. For air, it's approximately 1, and for water, it's 1.5. We also know the angle alpha, since it's the angle of incidence, and when we have an angle, we can easily calculate its sign, so we're left with just one unknown, the angle beta. So, with just some simple algebra, we can also calculate it, hence predicting the path of the refracted ray of light. Now back to coding, we need to define a float for the angle of incidence, and for animating the light, we need an animation speed, which is how fast the angle changes. For now, we'll set it to 0.5 so that our angle will increase by 0.5 degrees each frame. We also need to set the length of the light ray for later use when we're going to draw on the screen. To separate the two mediums, we'll create a list which stores 2 points. The first at 0300, so it's on the left center of the screen, and the second at 900 300, so it's at the right center of the screen. Once we connect these 2 points, we get a horizontal line. To understand better, we're gonna be naming a couple of points. A is at the top left corner of the screen, B is in the middle of the screen. A and B together create the ray of incidence. We just need to change the position of A later on according to the angle alpha. We then need to create a vertical line at the center of the screen, which is gonna act as our normal line. Lastly, we need one more point, C, which is the end of the refracted ray. For now, we'll just set its x to 0 and its y to 600. Now we need to initialize Pygame with this built-in command, and I have made a list of a couple of mediums and their refractive indices, and we'll define N1 and N2, the refractive indices of our two mediums. Finally, we'll set up our window by giving it a caption, a width and a height, and a background color and calling an update on it. Now that everything is set, we can start by creating a while loop and setting the clock to tick at 60. in order to get a fixed frame rate of 60 FPS. For keyboard inputs, we need to add a for event loop. The first if statement is useful to have so that we can exit and quit directly from the Pygame window. The other ones are optional, but for me I made it so that the escape button closes the window, the plus or equals button increases the angle of incidence, and the opposite for the minus button. This way we can easily go frame by frame and study exactly how the light refracts according to each angle of incidence. To create the animation, we just need to increase the angle of incidence by the speed of the animation, and if the angle grows over 90 or it decreases to under 0, we'll just change the sign of the animation speed, hence reversing the animation. In order to refract the light, we need to do some calculations on the coordinates of the points. So for that, we'll call a function to refract the light, and we'll define it later on. Finally, we need to redraw everything on the screen each frame. That's why we need to refill the window with the background color. Then, with the first two lines of code, we draw the vertical and horizontal grid lines. And with the second two lines of code, we draw the lines AB and BC, or the light ray before and after refraction. And of course, we won't forget to update the display in order to see everything. Moving on, it's time to define our refract light function and do some math, but don't worry, I have made it really easy. Firstly, we'll start with the x-coordinates of the point A. For that, we need the x-coords of the point B, which is in the middle of our screen, and we need to subtract the sine of the angle of incidence multiplied by the light ray length in order to correctly position it. We will then repeat the same steps for the y-coordinates of A, but instead of getting the sine of the angle, we need its cosine. I know you might not understand anything by now, so I'll explain what happened here. Basically, you need to go back to when you learned the trigonometric circle, the thing that everyone hates the most. Basically, a trigonometric circle has a radius of 1. The horizontal line is the line of cosines, and the vertical line is for the sines. Now, this circle has a special property that allows us to get the sine and cosine of any angle by just doing a projection on the lines respectively. So for example, if you need the sine of 45 degrees, you draw a line from the center to the edge of the circle with an angle of 45 degrees according to the horizontal line. We'll call this point A. And then you draw a perpendicular line from A to the cosine line. The distance between H and the center of the circle is the value of cosine 45 degrees. Now, what does this have to do with our code? Well, we can imagine B as the center of our circle with a radius of light ray length, which is equal to 200. Now, all we know about A is that it's a point on the circle, and that the line AB forms an angle with the vertical. But which angle? That's right, the angle of incidence, or alpha. Now, all that is left to do is to use these informations to calculate the coordinates of A. We'll start with its x-coordinates. And to make things easier, so that we don't have to deal with trigonometric quadrants, we'll rotate our circle. This way, the vertical line is the line of cosine, and the other one is for the sines. Now, as we learned from our previous lesson, to get the sine of an angle, we project the point A on the sine axis. But in our case, we need to do something different. We actually have the sine of the angle, and we need to calculate this distance, which will give us the x-coordinate of A. And it's really simple to do so. Since we have the sine of the angle, we just need to multiply it by the radius. And now we know A's x-coordinate, but not the final one, because in our calculations, the origin of our graph was the point P. So to fix that, we just need to calculate the new coordinates of A relative to the real origin of our screen. And it's quite easy to do that. We just need to subtract the x-coordinates that we just calculated from the x-coordinates of the point B. And then we need to repeat the same thing but with the y-coordinates of A, but instead of using the sine, we need to use the cosine. And tada! Now you know your trigonometry. Oof! Anyways, enough with the yapping, let's do some more coding. For understanding better, we'll name our angle alpha. Now you remember Snell's law, right? Since we need to find the sine of beta, we'll just take everything to the other side. This way, we get a really clean one-step formula. Now we need to do some checks. If the result of that is under 1, then our calculations say that the refraction happens normally. So we set the angle beta to the arcsine result of sine beta and convert it to degrees. Now what about the other option, where the result of sine beta is bigger than 1? We can't just let our code crash, right? So that's why... Wait, what? There's something I didn't explain yet. Hold on. First of all, why would the result of sine beta ever be bigger than 1? Well, let's dissect the formula. We have sine alpha is always gonna be between -1 and 1, so there's no problem yet. n1 over n2. Oh wait, if n1 is less than n2, then we have no problem, and light is traveling from a low density medium to a higher density one. But if n2 is bigger than n1, for example, light is exiting from glass towards air, there is one thing that could potentially happen, and according to Murphy's law, anything that can happen will happen. So what happens when this happens? That's 5 happens, now 6. Back to our example. Light here is passing from inside the glass to the outside, and when it's happening, everything is fine, until our angle of incidence surpasses a critical angle, and light, for some reason, gets trapped inside, and does a phenomenon called total internal reflection. Now, our light ray will get trapped forever in the glass, with no way to exit, unless we decrease the angle of incidence again. So yeah, that's it. Once we surpass this angle, we can't keep on just bending the ray of light. We need to make it reflect inside of the first medium. Now, one thing about reflection is that it's really straightforward. The angle of incidence is equal to the angle of reflection. So if our light ray touches a surface with an angle of 45 degrees, it will reflect with an angle of 45 degrees on the opposite side. Voila, we're done with the physics. Now back again to the code. It's so easy to code this. Under our else statement, we just set the angle beta to 180 minus our angle alpha, which now makes our angles equal according to the vertical line. Finally, we need to set the coordinates of our point C by doing the same calculations we used on our point A. I certainly hope you haven't forgotten how that works. But this time, instead of subtracting, we need to addition, because our point C is to the right side of the point B, and in Pygame, the top left corner is 0, 0, and everything to the right is positive. Now we just need to do some printing to the console, that way we know our angles. And now we're done, let's run this bad boy. Okay, first we'll set the n1 and n2 equal to 1, this way light is traveling inside of air. And as you can see, there is no refraction or reflection. Now, for the second example, n1 is going to be air and n2 is going to be water. And as you can see, we reach a critical angle where the light is no longer capable of bending anymore. For the final example, we'll set n1 to be 1.36 for glass and n2 will be 1 for air. This way, we can see the total internal refraction. So we start by increasing the angle and everything is good, but once the angle of incidence surpasses the critical angle, the light totally changes its direction, and now it's being reflected up there all inside the glass. Woo, physics is quite interesting, but that's enough for today. I'm too tired for this, so I hope you are now more educated both in physics and Python. It's really cool that we can create such simulations in Python really easily. Thank you for watching and see you!